Good morning, learners and viewers. Welcome to the session of Management of Machines and Materials, MMPC 009. Today, we will be discussing about Unit 3, 4, and 5. We will continue from where we left in our last session. That was, we were talking about discussing about plant location. The following considerations are needed in a plant location: nearness to the raw material source, nearness to market or consumer, good transportation facility, availability of fuel and power, availability of water, cheap availability of land, suitable climatic conditions, construction cost, taxes and government regulations, and waste disposal and environmental regulations. These are basically for considerations which are required for a plant location. As far as facility location decision is concerned, it is strategic in nature, maybe for long term, and it's non-repetitive. And we have to see to the concept of a facility. Production operation of service system. This includes industries related to fertilizers, steel, cement, rice, milling, textile, jute, sugar mill, rubber beverages, refineries, thermal, hydroelectric, nuclear power, hospitals, blood banks, fire station, police stations, banks, post office, etc. What are the steps in the facility location study? First of all, it is the general territory selection phase, and the second one is exact site or community selection phase. There may be some cases where the overlapping of the consideration of the factors are there, because we can see over here, location factors are market, raw material, transportation, law and taxation, ecology and pollution. For phase one, we can say first four are there. And for phase two, the last three are there. We can see that overlapping is taking place in phase one and phase two for transportation and law and taxation. Subjective, qualitative, and semi quantitative techniques. First of all, we have to see the industry precedence. Certain area is suitable for particular type of industry. Preferential factor. One wishes to choose his or own city or state on the basis of some personal interest. Dominant factors. On the basis of some factors, location is decided. And if we talk about qualitative techniques, so under that, there are five methods. First one is equal weight method, variable weight method, weight rating method, factor point rating method, composite measure method. We will start with equal weights method. We could assign equal weights to all factors and evaluate each location along with the factor scale. For example, XYZ, a manufacturer of fabricated metal products, selected three factors by which to rate four sites. Each site was assigned a rating of 0 to 10 points for each factor. The sum of the assigned factors point constituted the site rating by which it could be compared to other sites. Here we can see a decision matrix is there. It is these are the four potential sites and three factors are considered. After the tabular formation, we found that site 3, that is S3, has the highest site rating of 24. Hence, we will select site 3. For variable weight method, this method could be utilized on account of giving equal weightage to all the factors. Hence, we could think of assigning variable weights to each of the factors and evaluating each location site along with the factor scale. Hence, Fi might be assigned 300 points, vector 2 might be assigned 100 points, vector 3 might be assigned 50 points. Thus, a total point score out of the maximum assigned to each of the factor for each possible location could be obtained, and then the site with the highest score would be the obvious choice. We can see over here again, decision matrix is from maximum points as it was set for site 1, it was 300, site 2, it was 100, and factor 3 was 50. So after placing, getting up the values, we found that site 2 has the highest site rating of 370. Hence, in this case, by with this method, we will be choosing site 2. Then comes weight cum rating method. We could have yet another method of evaluating a potential location site. We would assign variable weights to each factor. The locations are then rated by a common scale for each factor. The location point assignment for the factor is then obtained by multiplying the location rating for each factor by weight factor. For example, rating weight of 1 to 5 could be assigned to the three factors F1, that is labor climate, F2, community facilities, and F3 is power ability and reliability, as 5, 3, 2 respectively. Now, for each of the factor site S1, S2, S3, S4, they would receive 0 to 10 points. So we will see how. We have four potential sites, factor rating, weights are given. After calculation, we found that site 3 has the highest rating of 83. Hence, in this case, by this method, site 3 will be chosen. Then the method is factor point rating method. We establish a subjective scale common to all factors. Assign points against the subjective scale for each factor and assign the factor points of the subjective rating for each factor. For example, five subjective ratings poor, fair, adequate, good, and excellent were selected to be used in evaluating each site for each factor. For each of these factors, adequate was assigned a value 0 and then negative and positive weights were given to each factors. F1, water supply, F2, appearance of site, F3, supply of labor. So after that, this table matrix, or we can say matrix, was formed. The range between minimum and maximum weights assigned to each factor in effect weighs that factor against all factors in a manner equivalent to the method. 3. Described just previous to this one. Each location site S1 to S4 was then rated by selecting the applicable subjective rating for each factor for each location and an equivalent points of that subjective factor rating assigned to the factor. Now, after clubbing for the decision making matrix was formed, here we can see that site 3 with maximum score of 9 will be chosen. In most cases, hardly an attempt is made to establish a direct relationship between the site rating points value and the cost values. Usually, this is left to the management. Location break-even analysis. Sometimes it is useful to draw location break-even charts, which could aid in deciding which location would be optimal. The location of a tractor factory in South Delhi site will result in certain annual fixed cost, variable cost, and revenue. The figures would be different for South Bombay site. The fixed cost, variable cost, and price per unit for both sites is provided like this in this particular table. Here we can see this, that for South Delhi, fixed cost is 40 lakhs, variable cost is 30,000, and price per unit is 75,898. And for South Bombay, it is 60 lakhs, variable cost per unit is 24,000, and price per unit area, price per unit is 82,000. We assume that the expected sales volume is estimated by a market research team is 95. Graphical representation was formed for cost versus sales volume for South Delhi as well as for South Mumbai. The break-even point is defined to be the point or volume where the equal cost total cost equals total revenue. Thus, for each site S1 and S2, the break-even point can be determined by using the simple formula, which is break-even volume (BE) is equal to fixed cost divided by revenue per unit minus variable cost per unit. So here we see that after calculating for South Delhi location S1, we got 88 tractors. And for South Bombay location S2, we got 104 tractors. Now we see that what would be the profit or loss for the two sites at the expected volume of 95 units. So this is the comparison. Cost is fixed plus variable, that is 68 lakhs 50,000. And for Bombay, it is 82 lakhs 80,000. Revenue is 75,898 into 95, which comes out to be 72 lakhs 10,310. And similarly, the revenue for Mumbai comes out to be 77 lakhs 90,000. If we talk about the profit and loss, so here we can see that for Delhi, we have a profit of 1 lakh 80,000, whereas for Bombay, we have a loss of 4 lakh 90,000. Now, how the conclusion is drawn. South Delhi site is preferable, even though the revenues are lower. Hence, the company will use money by locating the plant in Bombay. Quantitative model in facility location. First one is median model, second one is gravity model, third one is composite location model, two, and Bridgman's dimensional analysis. These are some of the case examples what we will be discussing: steel plant, cement plants, fertilizers, machine tool industry, nuclear power station. We talk about steel plants. Most of the steel plants lie along the Bihar, Bengal, and Orissa belt. It is always economical to transport the finished products rather than the raw material inputs like coal, limestone, and iron ore because during production, considerable weight reduction is involved. It is also near to port for easy import and export exercise. We talk about cement plants. Raw material lose weight significantly in the process of transformation. Cement plants are near to limestone and coal deposits. Fertilizer industry. Fertilizer plants are located near the raw materials. In case raw material has to be imported, then these plants are required to be located near the port. Machine tool industries. Proximity to the source of raw material is not very significant. Number of other factors such as market and infrastructures comes into the picture. And if we talk about nuclear power stations, it is no doubt a difficult decision. Lot of water is required for that means we have to see the availability of water, environmental problem, availability of infrastructure, and screening process is required. Now we move to unit 4, that is facility layout and material handling. Facility layout refers to an optimum arrangement of different facilities including man, machine, equipment, material, etc. Since a layout once implemented cannot be easily changed and cost of such a change are substantial, the facilities layout is a strategic decision. A poor layout will result in continuous losses in terms of higher efforts for material handling, more scrap, and rework, poor service, space utilization, etc. Hence, we need to analyze and design a sound plant layout that can hardly be ever emphasized. Layout problems occur because of many developments, including change in product design, introduction of new product, obsolescence of facilities,
ब्रेकफास्ट साथ में करेंगे, ठीक है? मैं 10:30 तक पहुंच जाऊंगा, ऐसा कुछ।
पाँच मिनट पहले वाला। इससे 5 मिनट पहले यही स्लाइड चल रही थी 5 मिनट पहले।
नहीं, कुछ और था। 5 मिनट पहले।
स्पीकर
वहाँ ठीक है, यहीं से the next part is types of plant layout. We start with fixed position or project layout. This is also called the project type of layout. In this type of layout, the material or major components remain in a fixed location, and tools, machinery, men, and other materials are brought to this location. This type of layout is suitable when one or a few pieces of identical heavy products are to be manufactured and when the assembly consists of large number of heavy parts. The cost of transportation of these parts is very high. We can best example is shipbuilding yard. Second one is process layout. Process layout is recommended for batch production. All machines performing similar type of operations are grouped at one location in the process layout. For example, all lathes in milling machines are grouped in the shop, will be clustered in like groups. Process layout is normally used when the production volume is not sufficient to justify a product layout. Third one is product layout. In this type of layout, machines and auxiliary services are located according to the process sequence of the product. If the volume of production of one or more product is large, the facilities can be arranged to achieve efficient flow of materials and lower cost per unit. Special purpose machines are used which perform the required function quickly and reliably. Fourth one is combination layout. A combination of process and product layouts combines the advantages of both type of layouts. A combination layout is possible where an item is being made in different types and sizes. Here, machinery is arranged in a process layout, but the process grouping is then arranged in a sequence to manufacture various types and sizes of the product. It is to be noted that the sequence of operations remains same with the variety of products and sizes. Combination layout for making different types and sizes of gears. This is basically an example which is being depicted over here. Group technology layout. Group technology is the analysis and comparison of items to group them into families with similar characteristics. The application of group technology involves two basic steps. The first step is to determine component families or groups, and the second step in applying group technology is to arrange the plant equipments used to process a particular family of components. This represents small plants within the plants. It reduces the setup time. Group layout is a combination of product layout and process layout. It combines the advantages of both layout system. If there are M machines and N components in a group layout technology, the M machines and N components will be divided into number of machine component cells, which we call them as groups, such that all components assigned to a cell are almost processed minimize the sum of the cost of the transportation and the cost of equipment. So this is called as multi-objective layout. Here we can see that what is group layout or cellular layout, how the machines or the process is being performed on a particular job. There are different production processes. If we talk about production process, because here we can see that depending upon the nature of the product to be processed, we can identify the production process. Production systems are mass or continuous, batch, job, discrete batch. If it, we will be comparing them in the terms of their volume, variety, and the type of layout required. If the one here, the one in mass production system, volume is very high, variety is very low, and we have to use product type layout. For batch, volume is low, variety is high, so we will be using process. For job type, the volume is very low, but the variety is very high. Here, again, we will be using process type. But in discrete batch, the volume is of middle level, and variety is again of the middle level, and we will be using cellular or group type of layout. What are the plant layout factors? The design of any layout is governed by the number of factors, and the best layout is one that optimizes all the factors. As discussed by Mudhar, the factors influencing any layout are categorized into the following eight groups. First one is material factor, which includes design, variety, quantity, and necessary operations and their sequence. Then, man factor. This includes direct workers, supervision, and self service help, safety, and manpower utilization. Third one is machinery factor, which includes process, producing equipments and tools, and their utilization. Next one is movement factor, which includes inter and intra-departmental transport and handling at various operations, storages, and inspection. The material handling equipments. Waiting factor includes permanent and temporary shortages and delays and their locations. Next one is service factor, which includes service relating to employee facilities such as parking, lot, locker room, toilet, and waiting room, etc. Service relating to material in terms of quality, production control, scheduling, dispatching, waste control, and service related to machinery such as maintenance. All these factors are to be considered. The building factor, which includes outside and inside building, features and utility distribution and equipments. The next one is the change factor, which includes versatility, flexibility, and expansion. What are the design procedures for layout? We have four phases in that. First one is location. Phase two is general overall layout. Phase three is detailed layout, and the phase four is installation. Systematic layout planning, we call it SLP. Here, the flow of material is second one is flow process chart, which is related to operations, transportation, inspection, storage, and delays. Third part is travel chart, from which part to the last part has to be included. Step 2 is activity relationship. Step 3 is relationship diagram, which depicts five things: absolutely essential commodity, essential one, important, ordinary, and unimportant. Step 4 is space requirement. 5. Space available. 6. Space relationship diagram. 7. Modifying considerations. 8. Practical limitations. 9. Develop layout alternatives. And step 10 is evaluation of what we have found. Here we can see that in short, what is this SLP is. Input data and activities start from the top. It all move towards the bottom as we discussed 10 points. So step 1 to 5 are for analysis. Step 6 to 9 is for search, and after evaluation, the selection is done. Application of quantitative techniques. The technique of operation research can be applied to quantitatively analyze the layout problems, particularly in terms of material flow. Some of the important techniques that have been applied by different researchers in the field of layout planning are linear programming, transportation algorithm, transshipment problem, assignment problem, traveling salesman problem, dynamic programming, VM theory, and simulation. All these topics are related to operation research. Linear programming is used when there is a linear objective function which has to be maximized or minimized subject to certain linear constraints. In the layout design, the objective is to minimize the material handling, transportation, and shipment problems are special cases of linear programming. Further, to meet the multiple objectives of layout planning, attempts have also been made to apply goal programming as a technique of multi-criteria decision making. Space determination and area location. The requirement of space by a facility bears a close relationship of equipments, materials, personnel, and activities. Two major methods that are being used for space calculation are space based on present layout and production center method. As far as space based on present layout is concerned, this approach is suitable when the proposed layout is to be developed for an existing product. While determining the space, consideration should be given to space required for the following. Number one, operating equipments. Number two, storage. Number three, service facilities. And number four, operators. Allowance must be made for space between machines for operator movement, working process, access of materials, handlers, and maintenance personnel, etc. If we talk about production center method, the space for each production center is determined including the space of machine, tool cabinets, worked and unworked parts, access to the site, and maintenance. In this method, actual arrangement of equipment is considered for space calculation. The departmental space is calculated by multiplying it with the number of production centers in that department. Computerized layout planning. Everything is being performed, designing, machining is being done by the help of computers. So planning is also being done by, and that too of layout is being done by computers. We have, if we talk about construction programs, so we use core lab, that is computerized relationship layout planning based on maximum closeness rating. Second one is LDAP. LDAP is automated layout design program based on maximum closeness rating. If we talk about improvements program, that includes CRAFT. CRAFT is computerized relative allocation of facilities technique, which is based on minimum material handling cost. Now we move to material handling systems. Material handling is a system which forms the various factors of movement, transfer, warehousing, in-process handling, and shipping into one independent cycle, considering the most economical solution for the respective plant. Objectives and functions. The basic goal of material handling is to minimize the production cost. And general objectives are to reduce the cost by decreasing inventories, minimizing the distance to be handled, and increasing productivity, to increase the equipment and space utilization, to minimize the waste during handling, to improve the working condition, and to improve the customer service. Basic material handling systems. First is equipment oriented systems. Depending upon the type of equipment used, there are several systems such as overhead system, conveyor system, tractor trailer system, forklift truck and pallet system, industrial truck system, and underground systems. Second is material oriented systems. They have following types: unit handling system, bulk handling system, and liquid handling system. Third one is method oriented systems. Here, according to this method of handling and the method of production, the material handling systems can be manual systems, mechanized or automated systems, job shop handling systems, and mass production handling system. The fourth one is function oriented system. The system can be defined according to the material handling performed as transportation system, conveying system, transferring system, and elevating system. Material handling equipment. We'll start with conveyors. These are gravity or powered devices commonly used for moving uniform load from one point to another through fixed paths, where the primary function is conveying. Commonly used equipment under this category are belt conveyor, roller conveyor, chain conveyor, bucket conveyor. Second one is cranes, elevators, and posts. These are overhead devices used for moving varying loads intermediately between points within an area, fixed by the supporting and binding rails, where the primary function is transferring or elevating. Some common examples are overhead drilling cranes, elevators, hoists, stacker crane, monorail, industrial trucks and vehicles. These are hand operated or powered mesh vehicles used for movement of uniform or mixed loads intermediately over the various paths, having suitable running surfaces and clearances where the primary function is maneuvering or transporting. These includes forklift truck, platform truck, industrial tractors and trailers, industrial cars, two-wheeled hand truck or trolley or hand stacker. Auxiliary equipments. These are the devices or attachments used with handling equipments to make their use more effective and versatile. Some common examples are ramps, positioners, pallets and skids, pallet loader and unloader, lift truck attachments, containers. Now, moving further, we move to Unit 5, that is related to planning and control for mass production. We will be talking about kinds of production system, flow shop, job shop, and projects. Types of manufacturing system. The production which a company uses depend upon the product that is offered to the customer. Make to stock production. Here, the products are manufactured and placed in stock before the customer's orders are received. For example, bearing, nut, bolts, etc. Second one is made to order production. Here, the company makes the product to order and manufactures the product after the receipt of the customer order. What are the different types of production? Basically, by this, we can see that there are three basic types of production system. First one is job type. Second one we can call as mass production, and the third one is batch production. Here we see what are the different types of production and how they are related. As if we talk about job production, one or few quantities of product designed and produced within fixed time and cost. High variety and low volume is there. Highly skilled labor is required. Large WIP is there. General purpose machines are required. And we have difficulty in planning, scheduling, and coordination. If we talk about batch production, here manufacturing of limited number of products at regular interval are stocked at warehouse or awaiting sales. Here we have short production runs, more number of setups are required, plant and machinery is flexible, large WIP is there, flexible material handling system is used, and this is basically applicable for pharma products, chemical industry. Now, if we talk about mass production, manufacturers several standard products produced and stocked at finished goods waiting to be dispatched. Here, the flow of material is continuous. SPM, that means special purpose machines are used. Short cycle time is there. High inventory of raw material is there. It's less flexibility of equipment and machines. And relative lower skilled labor is required. In which industry it is applicable? It is in the industry is related to plastic goods, assembly shop of automobiles. Now, when to go for mass production. It is generally agreed that mass production is justified only when production quantities are large and product variety is small. The ideal situation for mass production would be when large volumes of one product without any change in design are to be produced continuously for an extended period of time. If the rate of demand is greater than or equal to production rate, mass or continuous production should be sustained. And if the rate of demand is less than the production rate, then batch production with suitable inventory buildups can be resorted to. As a manager of a plant, you have to determine whether you would purchase a component part or make it in the plant. You can purchase the item at rupees 10 per piece with an investment equivalent to an annual fixed cost of rupees 20,000 and a variable cost of rupees 2.5 per piece. An assembly line can be set up to manufacture this part. The third option opens to use to make the part at an individual station with an annual fixed cost of rupees 10,000 and a variable cost of rupees 5 apiece. Assuming that annual demand is expected to be around 3,500 units, which alternative would you suggest? The choice from the three alternative purchase products produced at individual station or employ an assembly line for production. Three stages are there. And we are converting this into a mathematical relation. If Q is the quantity purchased or produced, the total cost equals part purchased, that is IUQ, part produced, that is 10,000 plus 5Q, and the part produced on assembly line, it is 20,000 plus 2.5Q. These cost functions are plotted, and the break-even point at quantity level of 2,000 and 4,000 reveals the following decision rules. For annual requirement of, after plotting of the graph, for annual requirement in the range 0 to 2,000, it is cheapest to buy. For annual requirements in the range of 2,000 to 4,000, it is cheapest to produce on individual station. And only for annual requirement of 4,000 or more, assembly line is justified. Thus, for an annual requirement of 3,500, you should not recommend the installation of assembly line. What are the features of mass production system? Advantages: a smooth flow of material from one workstation to the next in a logical order. Although straight line flow is common, other patterns of flow exhibited in figure are also employed when constraints of space or movement is there. Straight lines, U-type, serpentine, S-type. It's zigzagging. Since the one from one process is fed directly into the next, small in-process inventories result. Total production time per unit is short. Since the workstations are located so as to minimize distances between consecutive operations, material handling is reduced. Little skill is required usually by operators at the production line. Hence, training is simple, short, and inexpensive. Simple production planning and control systems are possible. Less space is required by work in transit and for temporary storage. And if we talk about disadvantages, a breakdown of any work machine may lead to complete stoppage of the line that follows the machine. Hence, maintenance and repair here is a challenging job. Since the product dictates the layout, changes in product design may require major changes in the layout. This is often expressed by saying that assembly lines are inflexible. The space of production is determined by the slowest or bottleneck machine. Line balancing proves to be a major problem with mass manufacture on assembly lines. Supervision in general, rather than specialized, as the supervisor on the line is looking after diverse machines on the line. Generally, high investments are required, owing it to the specialized nature of the machines and their possible duplication on the line. Assembly lines and fabrication lines. The term assembly line indicates a production line made up of purely assembly operations. The assembly operation under consideration involves the arrival of individual component parts at the workplace and the departure of these parts fastened together in the form of an assembly or subassembly. The term fabrication line, on the other hand, implies a production line made up of operations that form or change the physical or sometimes chemical characteristics of the product involved. Machining or heat treatment would fall into these operations. There are two types of line balancing problems. First one is assembly line balancing, and the second one is fabricating line balancing. Although there are similarities between the problem of assembly line balancing and that of fabrication, the problem of balancing a fabrication line or machine line is somewhat more difficult than the assembly of line balancing problem. It is not so easy to divide operations into relatively small elements or for regrouping. The precedence restrictions are generally tighter in the fabrication line. Some methods by which the balance of fabrication operation times can be achieved are changing machine speeds, using slower machines on overtime, providing a buffer of semi-finished parts at appropriate places. Fourth one is using mechanical devices for diverting parts. And the fifth one is improvement of methods improvement. How the designing of an assembly line is done. The work element which has to be established through the division of labor principle are assigned to work stations so that all stations have nearly an equal amount of work to do. Each worker at his or her station is assigned certain of the work elements. The worker performs them repeatedly on each production unit as it passes the station. The assembly line balancing problem is generally one of minimizing the total amount of ideal time or equivalently minimizing the total number of operators to do a given amount of work at a given assembly line speed. This is also known as minimizing the balance delay. Now the thing is that what is meant by balance delay? Balance delay is defined as the amount of ideal time for the entire assembly line as a fraction of total working time resulting from unequal task time assigned to various stations. After studying the variation of idle times and station caused by different assembly line balances, concluded that high balance delay for an assembly line system for a specific product is caused by wide range of work element times, a large amount of inflexible line mechanization, and indiscriminate choice of cycle time. Division of work into parts, the precedence diagram. The total job to be done on assembly is divided into work elements. A diagram that describes the order in which the work element should be performed is called a precedence diagram. This figure shows the precedence diagram of an assembly with 12 workstations. Note that 2 and 4 cannot begin until task 1 is complete, as far what the diagram depicts. Here we can see that there are 12 circles, 12 stations are there, and how the material is moving, it is depicted by the arrow. And dotted lines, boxes, depicts the stations, that how they are grouped. Moreover, there is no restriction on whether task 2 is done first or task 4 is done first. These two tasks are unrelated, meaning thereby that they can be done in parallel or even with partial overlap. A task may well have more than one intermediate immediate procedures. For example, in the precision diagram or figure, task 12 has three immediate procedures and cannot begin until all the three work elements, that is 8, 9, and 11, are completed. Grouping of tasks for workstations and efficiency criteria. Depending on the desired production rate of the line, the cycle time, that is CT, or the time between the completion of two successive assemblies can be determined. This determines the conveyor speed in the assembly line or in the time allocated to each operator to complete his share of work in a manual line. The individual work element or task are then grouped into workstations such that the station time, which is the sum of the times of the work element performed at that station and should not exceed the cycle time. The precedence restriction implied by the precision diagrams are not violated. There are many possible ways to group these tasks, keeping the above restrictions in mind, and we often use certain like line efficiency, balance delay, and smoothness index to measure how good or bad a particular grouping is. We'll see line balancing methods. First one is Kilbridge and Wester method. They propose that number are assigned to each operation, describing how many procedures it has. Operations with the lowest predecessor number are assigned first to the workstation. The procedure consists of the following steps. Construct the precision diagram for the work element. In the precision diagram, list in column 1 all work elements that need not follow others. In column 2, list work elements that must flow or follow those in column 1. Continue to the other columns in the same way. Then the second thing is select a feasible cycle time. It is done by Tmax should be less than Ct, should be less than the total complete time, cycle time. Assign work elements to the station such that the sum of the elemental time does not exceed the cycle time. This assignment proceeds from column 1 to 2 and so on, breaking intra-column ties using the criteria of maximum number of procedures. Delete the assigned elements from the total number of work elements and repeat step 3. If the station time exceeds the cycle time due to the inclusion of certain work element, this work element should be assigned to the next station. So we have to repeat 3 and 5 until all units are assigned. Now we take this example. Design an assembly line for a cycle time of 10 minutes for the following 12 elements, and we have to use Kilbridge-Wester method. Here we can see that there are 12 elements, immediate procedures are given, and the duration of time is given. Now, when we are plotting this, we have to start with element 1. After element 1, we can see that element 2 is there, 3 is there. Now the thing is that how they have to be planned. We can see over here, we have to see the immediate procedures of that element. We started with 1, 2. Immediate procedure is 1. And for 3, immediate procedure is 2. That means 1, 2, 3 will be at the top. And as we move on to element 4, we see that immediate procedure is 1. So that means it will come down. And similarly, following all these, we have to form this procedure diagram. And on the elements or what we have written in circle, we have to write their time duration. So we can see that a number is there, 5, 3, 2. Similarly, all the duration in minutes are written on it. First of all the precision diagram is completed as shown as we have discussed. Grouping is done primarily as we have done as per the diagram what we found. So these dotted boxes are clubbed. That means the grouping has been done. Now, how the calculation or the time or the ideal time or the total time is calculated. Station 1, element 1, time is 5. Total time for the station will be 5 and the ideal time will be 10 minus 5 because total time was 10 minutes. For second group, there are two elements 2 and 4. The respective time is there. We are going to club them. So we got 6. We have to subtract this 6 from 10. We get 4. That means for 4 minutes this machine was idle. Group 3, we have 3 and 5 elements and the total time is 10. And if we subtract it from the total time, the idle time is 0. Similarly, it is performed for all the groups. And total times comes out to be 50 minutes. With this, we will be concluding today's session and we will be no doubt continuing with this topic in our next session.